high temperature electrochemistry and its applications. So first I'm going to talk about the coulometric titration, how it can be used to estimate the stability and determine the defect chemistry of the oxide materials. And then from defect chemistry, from the high temperature, from the isotherm, how we can estimate the thermodynamic properties such as enthalpy of oxygen vacancy formation and the entropy of oxygen vacancy formation. And then further we go for the that is the application of electrochemistry in exsolution process. And later on, I'm going to introduce the status of proton conducting solid oxide fuel cells and their development. So the physical and electrochemical properties of solid or any oxides primarily depend on the defects and the oxygen vacancies present in the metal oxides. So with oxygen non-stoichiometry, and that is the oxygen isotherm. That is the oxygen isotherm is simply is plotted here. That is the in x-axis that the function of partial pressure, and then in the y-axis is the defects, that is the oxygen non-stoichiometry with respect to the temperature. So from the oxygen isotherm model, we can compute or calculate the defect concentration in the metal oxides for better understanding the charge and mass transport phenomena in the metal oxide. Here is the typical oxygen isotherm. I will come to explain later on this figure later. So first, let's just consider the metal oxide is in equilibrium with the atmospheric gas to form the non-stoichiometric metal oxides. So in order to be in equilibrium, the chemical potential of the metal and then oxygen potential of oxide in the metal oxide and then oxygen potential in the gaseous should be equal. So what are the ways we can determine the oxygen potential of this one is simple technique is the coulometric titration. Other modern ways are like using the thermogravimetric analysis or synchrotron measurements. We can estimate the chemical potential of oxygen here. So in coulometric titration is based on the measurement of chemical potential of oxygen in gaseous phase, which is in thermodynamically equilibrium with the oxide, which is the sample. So the schematics of coulometric titration setup is shown here. Simply, an oxygen ion conducting tube is be taken there. That's a yttria stabilized zirconia tube, and then the inner and outer walls are painted with a silver paste, and then to measure the potential across the tube. And then after keeping the sample, both ends were sealed. After raising the sample, we can measure the oxygen potential across the tube. So now the change in amount of oxygen inside the tube is given by passing the current for certain amount of time. That is the T and T test. After passing the time, the change in the amount of oxygen in the gaseous phase is given by delta Ng, and then the change in the amount of oxygen in the sample is given by delta Ns. So finally, the change in the oxygen non-stoichiometry, that is delta is given by this equation. So here the PO2 and then T is the temperature and pressure, partial pressure of oxygen, initial and final states. So by finally the partial pressure inside the cell is calculated using the Nernst equation. We know that the potential of the cell, that is the potential across the tube. We know the gas constant, temperature, Faraday's constant, and then the PO2 reference is often we use the cell in air conditions. So PO2 reference will be 0.209 atm, so that we can calculate the PO2 inside the cell. So this can be simply said as typical oxygen isotherm is shown here. In order to understand for layman's language, the sample is kept inside the tube, and then we allow to breathe the oxygen. So we calculate the breathing by the potential across the cell, so that we can estimate the amount of oxygen gone into the sample or gone out of the sample. So in x-axis we plot the log PO2 as a partial log PO partial pressure in log scale. In y-axis the change in oxygen non-stoichiometry. So typically in simple perovskite oxides, 3 is the stoichiometric point. From there it can either oxygen excess or it can be oxygen deficient. From this plot, we can estimate the stability of an oxide material, or we can visualize the stability or measure the stability of the oxide materials. At the same time, we can construct the defect model, the defect species, what are the defect species involved in the metal oxides, and then we can estimate the thermodynamic properties such as partial molar enthalpy of oxygen vacancy and then partial molar entropy of oxygen vacancy formations. So in this figure, essentially we can see that 3 regions, that is the high PO2 region and then intermediate PO2 regions and then low PO2 regions. So in solid oxide fuel cell technology, at high PO2 regions, that is log PO2 minus 5, until this area, the cathode materials will be operated. And then in the low PO2 region, that is log PO2 minus 25, the anode material is operated, used. Here the typical example is lanthanum strontium scandium doped lanthanum strontium mangan oxide. So I compared let's go for first check the stability of the material. For comparison, I plotted here the stability or oxygen isotherm of LSM at 650 degrees Celsius. It's only stable at log 10 power PO2 minus 20. So it cannot be used as an anode material for solid oxide fuel cells because it will not be stable at typical anode operating condition is about at 650 degrees Celsius log PO2 minus 22. So in order to improve the stability, with a small doping of scandium, after small doping of the scandium at 650 degrees Celsius, the stability of the material is increased log from minus 20 to minus 25 by doing the coulometric titration. We can estimate the stability or we can measure the stability of the oxides. Here I compare the another stability of layered perovskite oxides. Another well-known material for solid oxide fuel cell cathode material is prismidium barium cobalt oxide, which is the layered perovskite oxides. At 650 degrees Celsius, it only stable at log PO2 minus 6 atm. But for longer operation, for more than 1000 hours, there will be change in the PO2, but it will not be always made at log PO2 minus 6. Due to change in the PO2, there may be a material undergo decomposition. To improve the stability of this material, then we can dope the small amount of iron in the cobalt side, and then we measure the coulometric oxygen stoichiometry. We found that the stability greatly increased from log 10 power minus 6 to minus 9. The PbCO and PbMn, this material both shares the same structure of the metal layer perovskite structure, but simply by changing the cobalt side to mangan side, we can greatly improve the stability of this structure of material from cathode operating regime to the anode operating regime. This material is now proposed as the alternative anode material for solid oxide fuel cells. So now I will show, I will talk about how the partial molar entropy and partial thermodynamic properties, the partial molar enthalpy will be calculated. So partial molar enthalpy is calculated using Gibbs-Helmholtz equations, and then partial molar entropy is calculated using Maxwell's relationship. So here at a particular delta, and then the pivot region, partial molar entropy is calculated. The physical meaning for the partial molar enthalpy is the energy required to create an oxygen vacancies. So let's compare the partial molar enthalpy of scandium doped LSM for 3 different conditions. There is 0.2 doping, 0.3 doping, and 0.4 doping. So compare here. So here energy for 0.2 doping, the energy required to create one oxygen is more compared to 0.04. So here we need more energy, here we need less energy. So here the shows the partial molar entropy. The physical meaning for partial molar entropy is the probability of finding oxygen vacancy in the perovskite lattice. So compared to 3 doping conditions, 0.2, 0.3, and 0.4 scandium doping, 0.2 doping shows that there is a higher probability of finding oxygen vacancy compared to 0.04 doping. Similarly, PbCO shows that prismidium barium cobalt oxide shows that less energy, sorry, more cobalt and iron doped PbCO shows requires more energy to create one oxygen vacancy compared to PbCO. Similarly, here in high PO2 region, we need less energy to create an oxygen vacancy compared to the low PO2 region in prismidium barium mangan oxide. The same way, the probability of finding oxygen vacancy here is higher. In prismidium barium cobalt oxide is lower here. In low PO2 region in prismidium barium mangan oxide, the probability of finding oxygen vacancy is lower. In high PO2 region, probability of finding oxygen vacancy is higher. Then I'm going to talk about the X solution, how the electrochemistry is applied to drive the X solutions. Nowadays, metal oxides are widely used in solid oxide fuel cell technologies and then other other energy conversion applications. So, in order to improve the performance of the electrode of the metal electrode, that is the metal oxide, we usually deposit some catalytic nanoparticles to improve the electrochemical performance. But due to under long time operation and then higher temperature, these nanoparticles will undergo some kind of agglomeration. Because of the agglomeration, particles becomes bigger and then the number of particles is reduced. Here I shown the typical example of oxide support where the nickel is deposited by infiltration technique, and then the initial scanning is taken. SEM image shows that the more number of nickel nanoparticles are deposited on the oxide material, and then with increasing the temperature and then longer operation, these nanoparticles agglomerate. Because of that, we lose the electrochemical performance. So then later on, Irwin from St. Andrews, he worked on extensively on nanoparticle exsolution. So exsolution is a process where the catalyst nanoparticles emerge spontaneously when exposed to reducing conditions in the reducing atmosphere. So here is the oxide support is prepared, and then when exposed to reducing conditions, the nanoparticles will emerge on the surface of the oxide. Since the nanoparticle is socketed here, it will not undergo any agglomeration. Because of that, we will not lose any catalytic performance or and then consequently the electrochemical performance. The schematic shows the exsolution process. First, the oxide material is prepared, then typically it was reduced in hydrogen, typically in 5% hydrogen at higher temperature from 700 to 900 degrees Celsius. Then metal nanoparticles spontaneously will emerge. So this can either done by non-stoichiometric oxide, we can prepare the non-stoichiometric oxide where A site is deficient, and then when exposed to reducing conditions, there will be change in the oxygen non-stoichiometry, because to maintain the charge neutrality, some of the B site element, that the stoichiometric element, is exhaled as a catalyst nanoparticles. Similar way, exsolution can also happen in the stoichiometric oxides. Under reduction conditions, some of the A site material and some of the B site material will exhaust. So what the driving, there are many ways we can drive the exsolution. One typical is the gas, by controlling the atmosphere and then temperature, or it can be the exsolution can be driven by strain in the sample, or it can be driven by the phase transition, or it can be driven by cation deficiency, or it can be driven by a topostatic ion exchange. The facility easy way is electrochemical switching. That is, by applying a certain potential on the electrode, we can selectively and then quickly emerge the nanoparticle on the surface of the electrode, compared to traditional, that is by reduction process. Here I shown the schematics of the solid oxide cells. This is the electrolyte, and then the air electrode, and this is the fuel electrode where we're going to do the exsolution. After this cell is this fuel electrode is exposed to 5% hydrogen, typical PO2 range of 10 power minus 19. So exsolution was happened. This image shows the exsolution, SEM image of exsolution after exsolution. So we can see that only small number of nanoparticles are exhaled, and then it takes very long time, more than 15 hours. So by in the same way, we can exsolute by electrochemical switching. And after preparing the cell, when exposed to 50% steam and then nitrogen, and by applying the small potential on the electrode, we can generate a partial pressure difference about 10 power minus 35 in ATM. Because of this high partial PO2 difference, exsolution was happened very quickly, and then see more number of particles are exhaled on the surface of the perovskite oxides. So here I compared the oxygen loss with respect to the time for reduction, and then with respect to reduction using electrochemical switching. So for reduction, it takes more than 15 hours to reach the equilibrium for exsolution. However, for electrochemical switching, by applying a small amount of voltage on the electrochemical cells, within 150 seconds, the whole nanoparticle is exhaled on the surface of the perovskite oxides. Next, I'm going to talk about the status and then development of proton-conducting solid oxide fuel cells. Now we recently recognize the use of renewable energy such as solar, wind energy, and then we need a modern ways to store the excess energy. One way can be done by in the batteries, but we can it should be reversible. So then the concept of reversible cells were introduced, where the excess energy can be stored in the form of fuel, and then whenever there is the depletion of energy, we can reverse the cell into cell, so that we feed the fuel to generate electricity. So this is the basic principle of proton-conducting solid oxide fuel cells. It's similar to other electrochemical cells. It essentially have three components: anode, electrolyte, and the cathode. Fuel is fed into the anode, and then it's converted to proton, and then goes to the cathode through the electrolyte, and then the electrons are moved in the external circuit, and then typically water is formed, or byproduct is formed in the cathode area. I think Stephen is already explained about the theoretical voltage potential. There will be some leak. This leak is due to either it can be a sealing problem of the solid oxide fuel cell, or it can be a electronic leakage across the electrolyte. and then we slowly draw the current. Because of that, there will be some slow reaction kinetics. Resistance will be formed. When still decreasing the voltage, we can draw the current at that in this region where the ohmic loss will be the higher, and then the lower voltage where the mass transfer resistance will be higher. So voltage loss are summarized here. It can be a fuel crossover, or it can be a finite reaction kinetics, or electrolyte resistance, the ohmic resistance, or the mass diffusion resistance. So various types of fuel cells are are classified based on the type of electrolyte. In solid oxide fuel cell technology, conventionally, yttria stabilized zirconia is an oxide ion conductor used as an electrolyte, where it requires 700 to 1000 degrees Celsius for operating temperature. By increasing the temperature, we can increase the fuel flexibility and efficiency, where we can use both hydrocarbon and hydrogen as the fuel here. But the problem is it requires more thermal energy, thermal management. Like operating at higher temperature, there will be a side reactions with other components of the fuel cells. So there is an immediate requirement to decrease the operating temperature of solid oxide fuel cells. So one way it can be done by decreasing the operating temperature of fuel cell by increasing the ionic conductivity of electrolyte. There are various materials available. One such material is a doped with barium zirconate, is a ceramic ceramic material which shows higher proton conductivity in intermediate temperature at about 500 to 250 degrees Celsius. So to still improve the proton conductivity in barium zirconate, we can typically dope with other dopants so that we can increase the oxygen vacancies. These vacancies filled by the OH groups for the proton conductions. So what are the advantage of proton conducting solid oxide fuel cells over the oxide ion conductor? Is the operation at it allows to operate at moderate temperatures. Because of that, the acrylic components will not be too hot. In solid oxide fuel oxide ion conducting solid oxide fuel cells usually cell operate at higher temperature. Because of that, there will be a side reaction between the anode and the cathode, or the electrodes with the electrolyte or other components of the fuel cell, such as current collecting issues will be there. So in proton conducting solid oxide fuel cell, there will be no problem on the fuel dilution. So the unreacted fuel can be recycled back into the proton conducting solid oxide fuel cells. But here in oxide ion conducting fuel cells, the fuel is converted to as a byproduct in the water. So fuel should be recycled to remove the water. There will be additional complexity. So until 2014, the material was like proton conductor although shows the higher ionic conductivity, but the performance of the fuel cell is not so high compared to the solid oxide fuel cells with oxide ion conductors. This is because the electrolytes react, that barium zirconate react with carbon dioxide and water to form the barium zirconate, barium carbonates. So another issue is like although the conductivity is higher, the ohmic resistance is much higher than the expected from the electrolyte, that barium zirconate, higher conductivity barium zirconate. So this is the expected ohmic resistance, and then we can see that there will be the high ohmic resistance is recorded for the fuel cell. And this may be due to the contact resistance, or it may be reacting with the nickel or poisoning. Because of various reasons, the proton conducting solid oxide fuel cell performance is not so good. So now we want to develop the proton conducting solid oxide fuel cells with a stable electrolyte. So one good candidate material is barium zirconate. It shows the excellent conductivity, but barium cerate shows a very reasonable conductivity. Both shows the poor grain boundary resistance, poor grain boundary conductivity, and both. Barium zirconate is very stable in carbon dioxide, but barium cerate will react with the carbon dioxide. So making a solid solution and then doping with YB and yttrium and yttrium, we can increase the stability of barium zirconate materials. And then here it shows the ionic conductivity of barium zirconate, Y-doped barium zirconate oxides, and then by small amount of doping in cerium, and then Y and YB doping, we can improve the conductivity. At the same time, stability was greatly improved in carbon dioxide atmosphere. So now we developed the good electrolyte. Then we have to think about like developing a good cathode. So let's compare the good cathode. I mean, let's compare the proton conducting oxide cathode and then oxide ion conducting electrode. So here the for oxygen diffusion reaction, oxygen reduction reaction happens at the cathode, and then oxide ion is moved in the electrolyte and in the anode region. It reacts with the hydrogen to form the water. So the cathode here is the mixed conductor of both oxide ion and the electron. But we use the mixed conductor as the cathode for proton conducting solid oxide fuel cells. Since the water is formed at the cathode, water is formed at the interface. Because of that, there will be a higher chance of delamination will happen. So we need to develop a new cathode materials that should not affect the interface between the electrolyte and the cathode. So we need to develop a cathode material that should be a triple conductor that should conduct both oxide ion, proton, and electron to form the water on the surface of the cathode. So many materials were proposed as a cathode material for proton conducting solid oxide fuel cells with simple and double perovskites. And recently, praseodymium, barium, strontium, cobalt iron oxide (PbSCF) as used as the proton conducting solid oxide cathode material in proton conducting solid oxide fuel cells. And then NbSCF. This material also used as a cathode material in proton conducting oxide fuel cells, and then shows excellent or good performance in reasonable performance in the proton conducting solid oxide fuel cells. Then the researchers have developed, fabricated the proton conducting solid oxide fuel cell with traditional ceramic processing method, where nickel and then doped barium zirconate as the electrolyte, and then the electrolyte, and then the composite of nickel and the barium zirconate anode and PbSCF cathode. In order to reduce the interfacial resistance and to improve the contact between the cathode and the electrolyte, they deposited a thin layer of like 100 micrometer PbSCF material here. So if this PbSCF material is not a triple conductor, it blocks the proton coming from the anode that moves through the electrolyte. Since it's a triple conductor, it allows the proton to conduct to the cathode where water is formed. If it is not a triple conductor, it would be a bad idea. There will be no electrochemical reaction happening here. But there are still debates are going on whether the perovskite materials are truly are having showing some proton conductivity. Then the research measured the electrochemical performance of proton conducting solid oxide fuel cells and the fuel cell mode at 650 degrees Celsius. It shows about like a 1.5 watts power density with the PLD layer. We can compare the power density, peak power density with and without PLD layers. Without PLD layers shows the lower electrochemical power density. This is maybe because of contact between the cathode and the electrolyte would be not good enough. And then they compare the ohmic resistance of proton conducting solid oxide fuel cell with PLD layer and without PLD layer, and then it shows that the ohmic resistance was greatly decreased with the PLD small layer of PbSCF cathode on the prepared by PLD. And then from 2008, now the solid proton conducting solid oxide fuel cell shows the record performance with a stable performance over 700 hours. There is no degradation. With this shows the maximum power density of 500 milliwatts per centimeter square. Then our objective, the main objective of the research community is to use the proton conducting solid oxide fuel cell in reversible mode. So first let's compare electrolysis in oxide ion conducting solid oxide fuel cells. So the thick layer is the fuel electrode, is made up of nickel and zirconium oxide. This is the electrolyte zirconium oxide, doped zirconium oxide, and here is the cathode. So when exposed to highest T, the nickel is higher chance to undergo oxidation. Because of that, there will be a microstructural change. Cell will decompose quickly. So in proton conducting solid oxide fuel cell, the nickel nickel electrode is not exposed to steam. Only steam is exposed to the fuel electrode, and that is the anode region here. Or for convenience, let's call this as the fuel electrode. And because of this, no water is found in the cathode compartment. The cell will be stable, and then they measure the electrochemical performance and the performance in electrolysis mode. The cell shows no degradation over 300 hours. And the next slide is like the main objective of the solid fuel cell community. They want to develop a reversible solid oxide fuel cells where we can operate the fuel cell and then electrolysis mode when switching back and forth. By reversible operation, it shows over 50 hours there is no degradation in fuel cell mode in both electrolysis mode. This can be operated in the this shows that there is a huge potential of proton conducting solid oxide fuel cells to use as a reversible battery or like a flow batteries. And then, yeah, this comes for the conclusion. Thank you.
Thanks, that was really fascinating. Who'd like to ask a question?
So yeah, hi, so just a quick question. So can you just go to the beginning? So you show some figures like the delta versus the partial pressure of oxygen. Yes, I just wonder how you determine the oxygen stoichiometry. So I mean, how you determine the delta, the value of delta here?
Delta?
Yeah.
Initial delta. I mean, in this region or like a...
Yeah. How you determine at each step, at each partial pressure of the oxygen, how you determine the delta here?
Yeah. First, we keep the sample inside the coulometric titration setup. We know the mass of the sample. We can calculate the initial oxygen inside the sample, and then we increase the temperature, right?
Yeah.
For higher temperature, for example, at 700 degrees Celsius, we measure the potential. So we know that what is the amount of oxygen in the sample. We know what is the amount of oxygen inside the tube by measuring the potential. After that, we can either pump in or pump out the oxygen. We can, for example, let's in this figure, we remove the oxygen from here. So removing the oxygen, that is pumping out the oxygen from the tube. Some of the oxygen is pumped out. After that, the sample will be in equilibrium. It goes for a breathing. Some of the oxygen from the sample is breathed out, and then it fills the tube. So now we measure the potential of the in the cell. So first the previous potential and the next potential is lower than the previous one, so that we know that some of the oxygen is how much oxygen we pumped out, how much oxygen came from the sample, and then from there we can calculate the delta.
Thank you. Thank you.
Thank you for the talk. It's a rather very general question. I'm curious for this exclusion technique. Like, is it only applicable for the perovskite, or it's a general approach for any oxide?
So general for any oxide, but there should be some window. There should be some window for removal of oxygen, and then since the oxygen is removed, there is an instability or change in the charge between the cation and the anion. Because of that, the exsolution will happen. So not all the materials will exsolve. So some of the materials are having, perovskites are having really high affinity towards the oxygen. It will not even increase the temperature, high reducing atmosphere. Okay. It will not give out the oxygen. Because of that, there won't be any exsolution. So it's like a trade-off between the oxygen non-stoichiometry and the stability of the sample.
Okay, yeah. I was just wondering, like, if like this is applicable for any precious metal, but I guess maybe no.
Yeah, we can. I mean, there are many reports started working on. So this is the nickel metal.
Yeah.
So think about like we dope platinum or palladium in this material. So all the materials, some of the materials only will exsolve towards the surface. By electrochemical pooling, we can exsolve all the material. I mean, what are the, for example, like X amount of material is dope inside the material. We can try to exsolve all the X amount of material from the perovskite lattice.
Okay, that was really fabulous. I was just thinking, like, the only issue I was imagining is that we might be lost like wasting some precious metal in the core. But if everything, all the platinum or everything like that, it can be exsolved. Yeah. Okay. Yeah. Thank you. That's really nice.
I have a quick question on that topic, actually. So I thought it was very neat what you were showing with the kind of electrochemical exsolution. So can you do that? So you're doing it essentially by kind of applying reducing potential. Yeah. Could you potentially exsolve oxide particles?
Oxide particles
instead of metal particles? Because in some cases, let's say, if you wanted to make one thing that would be really nice if you want to make a catalyst for oxygen evolution would be for let's say iridium or something like that. Is the metal is not usually stable. So if you kind of, you really need to be oxide to the core. But if you could kind of get iridium oxide nanoparticles exsolved and then kind of have a conducting support, so that would be really good.
Yeah, one way can do that is like if iridium metal is exsolved after that, we can keep this since the material is socketed.
Yeah.
So, for example, like these dots are the iridium.
Yeah.
It's after exalt we can expose to the atmosphere. We get higher oxygen condition, so that metal can oxidize.
Yeah.
Since the metal is socketed, it will not undergo any.
Because often what happens when you do that though is it doesn't form. And someone can correct me if I'm wrong, but often when you take metallic iridium and then you oxidize it, it's not as stable as when you grow it as an oxide in the first place, if you know what I mean, because I think that you still have some metallic iridium at the core and it'll tend to corrode out.
Okay.
But I don't know if that's that's what, at least what that's what we previously looked at kind of side effects of ruthenium nanoparticles, and they were also if they were metal at the beginning and then you oxidize them, it'd never be as stable as if you grew an oxide. But I might be wrong though.
But it again depends upon the thermodynamics of the material. For example, I try to exsolve the mangan on the surface of the perovskite, but it exsolved as a mangan oxide because the oxygen and the oxygen.
Which element was that?
Mangan. Okay. So it stays as a mangan oxide. The affinity towards the mangan oxide bonding is very strong.
Yeah.
Even if I apply the high potential or high reducing environment, I cannot strip off the oxygen from the mangan oxide. So it's again an intrinsic property of the.
Yeah, I understand. And what temperature did you do this electrochemical exsolution?
Here it's 700 degrees Celsius.
700, okay.
700 to 900 degrees Celsius.
Very interesting.
I just have one question about the cell setup that you did. That's actually rather engineering. So I was first of all wondering, I guess that's a bespoke cell, right? So you made it in-house.
Yeah.
Okay, so I'm not familiar if there are other alternative cells for the same work out there, but I was just wondering basically how you made the contacts and what metal did you use? I assume you use the metal. I'm not sure.
Making contacts.
Yes. So if you go into the cell that you had in the furnace.
Okay, so this is the electrode, and then for current collection we use the silver paste or gold paste. That's the current collecting.
Okay, so can you really quickly go into the setup that you had with the cell in the furnace?
Oh, okay.
All right. So I assume that there are some contacts within the tube furnace, right? Or they're outside?
This one?
No. So you have a current and the voltage going into the tube.
No, this is the potential to measure the across the tube. This is to measure the electrical conductivity of the sample.
But this is
the in-house
tube.
design. This is the in-house design. Usually there will be no electrical conductivity measurement here. So we can measure the conductivity as a function of PO2.
Okay, but technically you can measure the conductivity while you're heating up the sample, I imagine, right?
Yeah.
So I was actually wondering, how did you make the contacts then? So what metal did you use?
This here.
Yeah.
Silver paste.
Okay.
PT wire, and then we put a small amount of silver paste on the sample.
Okay. All right. And final question: you showed some current density graphs that were a little bit fluctuating. So I was wondering, how would you attribute this fluctuation to? I mean, where?
You mean here?
No, I think it's a little bit further down. This one, yeah.
So here.
Yes.
So this is the stability of the cell. So usually there will be while doing the stability, there will be silver wire is used as the contact. Due to some external disturbances from the environment, there will be fluctuation. That's the reason it comes from.
Yeah.
So if it's not somebody shaking the table or.
Okay. Got it.
That's the reason.
Okay, perfect. Thanks a lot.
Son, did you have a question?
Yeah. My plan is also on the cell, on the stoichiometric titration cell. I guess it's equation 6. I'd like to see which shows the delta calculation. Here you've got the change in oxygen, but you also have this term with integrating the current. So do I understand right that you're running current through the sample while doing this measurement?
Yeah.
And where's the counter electrode in that case? If I can put it that way.
So this is the reference electrode, the top one, and the bottom one is the counter electrode.
Okay, where's the working electrode then?
So this is just measure the potential and then apply the current to pump in and out the oxygen. We just measure the potential across the tube.
Yeah.
And then we apply the current to pump the oxygen in and out. It's a 2 electrode setup.
Apply current to. Okay, so the only way oxygen is getting into the tube is through. Thank you. Okay, now I understand the cell better.
There are 2 more electrodes on the sample inside the tube, which are doing a particular purpose.
Okay, do we have any more questions? Doesn't seem to be the case. Let's give both our speakers another applause.